right, thanks everyone. First of all, these slides are actually a Jupyter notebook in presentation mode. The link is up there. I recommend you check them out, follow along. Part of this being in presentation mode is I'm skipping a lot of the code. Part of that's because I have an hour, and part of it's because a lot of the code, once you've seen it, is relatively trivial to implement in Python. Like, there's great libraries, Python's great. So the really important part about this talk is about the person, the programmer, the data analyst, and how you look at your data. So there's two main talks to this, or there's two main parts to this talk, and they fit in nicely with, we had a nice lightning talk about the entire process and what happens before you get to that machine learning algorithm. So first is data cleaning or cleansing, preparing, scrubbing. So this is common to all data analysis. You have a data set, you have to make sure the data is correct. You have to make sure the data set is complete, there's nothing missing, there's nothing irrelevant in that data set. And then the second part, I'm kind of calling it data pre-processing, but it's essentially you've cleaned your data set, but you need to get it ready for whatever machine learning algorithm you're going to be using. So, as mentioned in the title of my talk, I love this phrase, garbage in, garbage out. We talk a lot about the machine learning algorithms and the math and how great and powerful they are, and they are great and they are powerful, but they will never be any better than the data you give to them. If the data is wrong, if the data doesn't have the information that you want to learn from, no algorithm is going to be able to learn from it. And you can get, if you have a powerful method or algorithm, you can get away with having some kind of CRUD in there. It might be able to recognize that this is CRUD on its own. But in leaving that in there, you've wasted computer cycles and resources and time that this machine had to try and figure out what is the relevant data when you could have just told it that before you gave it to the algorithm in the first place. So I have some kind of steps to machine learning. First is get your data set and understand it. You can't do a lot of this properly if you don't know what your data is. What features do you have? What do they represent? What do they mean? So once you have and understand your data set, you can clean it, create your training, testing, and validation data sets for your algorithm to use, do any data scaling or normalization and pre-processing you want to do, and then you want to select what information out of your data set is relevant to give to the classifier, and then you select the classifier that you want to use. So as I said, these are 3 notebooks. That was the shortest one. So I'm starting with data cleaning. And so my example data set, I've modified a version of the National Health and Nutrition Examination Survey. So they did some pre-processing to this data set before releasing it. I undid some of that to kind of show you some of the problems you can have in a data set. So this data is, it's in 2 different files, and it has demographic information and some body measurements like height, weight, head circumference of almost 10,000 people in total. So data cleaning is one of the first steps you want to do after you get your data set. And this includes things like formatting errors. If there's any text data, do some entries have extra white space that it wouldn't match up? Are there any misspellings in there? Incorrect types. Are you expecting a number and someone put their name in there? Any duplicate entries. You don't want any data to be duplicated. You don't want any person to be counted twice, because now they are twice as important as any other person in your data set or any other example. So you want to make sure that every entry is only in there exactly once. Dealing with missing data, if something wasn't recorded or it's lost from your data set, how do you handle that? There's also kind of nonsensical data entries. Anything, a negative age doesn't make any sense. We want to get things like that out of your data set. There can also be saturated or default data. So if you have a sensor or something that records, say you can only measure something up to 12 feet long, and anything longer that would also be 12 feet, even if it was actually 30 or 40. How do you deal with things like that? And then you can also have confidential information that you may want to consider removing from your data set if you don't think it's appropriate to share or show to anyone else. So one of the first things we want to do is we want to take a look at our data. So load it in with pandas, And we've got this nice data frame here with these lovely column names that don't mean anything to me. But you can see all the data is numeric, so we don't have any text data to deal with. We have all numbers, but we don't know what any of this means. So some basic formatting, as I said, it's all numeric. We don't have to worry about misspellings, white space, or data type, because it's all numeric. But those columns used coded names. So this is really convenient from a programming perspective. They're relatively short. There's no spaces or punctuation, but it's not readable. So for the purposes of this, I'm going to rename them by using the dataset codebook, looking up what they need. So this very intelligible RID statter is actually whether a person just completed a short interview or if they had a full exam, their gender, age, renaming everything, so that now when we look at this data at a glance, we can say, oh, I know what this is. This is, the coding for their age or their gender. So I also talked about duplicate entries. It's relatively easy to find. You can ask pandas, find all the duplicate IDs. Each ID number refers to a person. And there's different ways that you can find duplicates in your database. So one person, number 190, they have conflicting information. Are they 10 years old or are they 65 years old? The age column doesn't match. So unless you can find out who this person was and what their age really is, it's best to just get rid of these type of duplicates because you don't know what the problem was. That maybe it's two different people. Maybe they were accidentally recorded twice with a mistake in one of the entries. So you remove that. Another possible problem you can have is maybe the data is split between two entries. So one entry only has the age, the other entry has its value for the exam and the gender. So you can combine those two columns, or you can replace those two columns so that they have, it's one entry with that same data. The final example, the easiest example, subject 3, is just the same data in there twice. You can just drop the duplicates. Relatively easy to deal with. So once you have cleaned out your data, you would want to do the same thing to all of your data sets, and then you can merge them. So we also, for these same people, or most of the same people, we also have weight, height, and various body measurements. So we can load that in and join those two tables. And the important part is the subject number, so you want to make sure that you're joining on the person's ID, so that person 1's age is also lined up with person 1's weight. So as things go along, it gets a little more interesting. Dealing with missing data. There are a couple possible ways to deal with anything missing, any not a number entries that you might have. You can somehow find this missing data. So if you know how the data set was collected, if there were a bunch of surveys that were then entered into a database, maybe you can find the original survey for this person. Was there something wrong with that entry? Did it accidentally get skipped? As was mentioned earlier when talking about neural networks, sometimes you can replace it with another variable, like just the average value for that feature, and put that in for the missing variables. Another option, you could consider recoding not a number to another label that kind of indicates unknown. We don't know what this is. For some analyses, this might work. For others, you might want to just get rid of it anyway. And getting rid of this data brings me to, you have two primary choices. You can remove an entire feature, or you can remove specific examples. And that's going to depend on your particular data set. How important are different features to you, and how important is it to have a lot of different examples? So a good way to start with trying to figure this out in our data set is look at all of our columns, all of our features, and try and ask how many items are actually missing. So you can see there are a lot missing. Almost all of the values for head circumference are missing, 9,697. There are also a lot missing for education. Education is split into education level for children and education level for adults. It was recorded differently. But both of those columns have a lot of missing information. So as far as replacing the data, some of those doubled columns, like education, And then there is standing height and recumbent length, more for children. They don't stand yet, so just how long is the child. If we want to, we could combine those into single columns, getting rid of some of those not a number entries and preventing us from having to get rid of as much data. So it's relatively simple to do. Replace all the missing values for height with the recumbent length. And then if we can look at the code book for education and see how children education is coded, how adults are coded, recode them both to match, and combine them together. So now we have one education column and one column for height. And then when we look at the number of missing entries, the education only has under 2,000 entries missing now. So we've recovered a lot of information this way by combining our columns. But there's still head circumference and student status. There's a lot of information missing. And say I've talked to the person who got the data set and said, no, if that data is not there, there's no way to recover it. So then we want to talk about removing data. And because there's so few examples for those two features that are actually good data, we want to remove them. So here we remove the student status and the head circumference. But some of the other examples, like say there's only 1,000 missing or 700 missing, in those cases it makes more sense to remove the rows, so remove the actual individual people's entries if not all of their data is there. But when we're done with this, we have 5,543 examples remaining, but there's no not a number entries. So nonsensical entries are some of the most interesting ones to talk about. They're things where the data don't make sense. And as I mentioned before, as we go on, it's more and more important that you know about your data. So there's some trivial examples of what might be a nonsensical entry. If something can be labeled a 0 or 1, and you have a label of 3, that's clearly a mistake. If the age, weight, or height is less than 0, also clearly a mistake. So as an example here, we look at all, for anything that has a single label as opposed to a continuous value, we look at all the values that are recorded. And I would like to point out marital status has a value of 8. So there's a lot of different, married, divorced, unknown. These are unknown and refused. But this 8 right here, if you look up the official code book for what this data set is and what it represents, there's no 8. 8 doesn't mean anything. So anything with an invalid label you would want to get rid of. We can also remove those refused and unknown. Like I said, in a lot of analyses, they don't necessarily mean anything. They're very similar to just not a number entries. We can get rid of those as well. And so I'd mentioned continuous values, age and weight less than 0. Also, anywhere where the weight is greater than 635 kilograms, which Google says is the heaviest person on record. Figure anything higher than that is safe to get rid of. And these are kind of obvious examples, like almost any person you go up to is like, does it make sense for someone to have a negative age? And they would say, no, you want to get rid of it. But as you learn more about your data set, there may be things that are not obvious. So if you have a timestamp of when your data was recorded, and it says that it was recorded at 1:32 in the afternoon, that might seem fine at first glance until you think about the fact that your data set was supposed to record this value every hour on the hour. So what was it doing recording at 1:33 in the afternoon? That's not something that you would see just by glancing at the data set. That's something you would have to know about what your data is supposed to mean. Other examples would be if you know that you have a device and it records to the nearest, nearest tenth, 0.1, and you have some entries with a lot of decimal places, like 0.32. That's another thing that might make you look at your data and like, my sensor can't record to this value. That doesn't make any sense. How did this number get here? And it's another thing that would make you want to look at your data set in more detail. Another thing that might come up in your data is saturation. So this can be from a sensor, say a temperature sensor that can't record any lower or higher than a certain temperature. In our case, it's a survey, and everyone who was 85 or older were all recorded at 85. So those are both ideas of both examples of saturation. So you can find how many are at any saturation limits you know. Anything that's over the saturation limit, you can, again, immediately conclude is wrong. Things on the limit are a little trickier, because you don't know what they are. Anyone here who's listed as 85, they could be 85. They could be 90. They could be 110. So, and it's going to depend on what kind of analysis you're trying to run. How important is it that you know exactly how old a person is? And how important is it that you know exactly how old a person is in that age range? So in this particular example, I'm only getting rid of anything over 85, because that's clearly a mistake. But it would also be totally valid to get rid of anyone 85 and older for your analysis. And so that is the end of my overview on data cleaning. And I'll move on to the machine learning lab. But are there any questions about the initial data cleaning? So the goal here is to understand your data set and to get rid of all of the wrong and incomplete data. Yeah, so there's actually a lot of opinions on things like, so the question was, what do you do about obvious outliers? So if someone is 5 years old and has a very high weight, this is something that, is impractical or if not impossible. And there's a lot of opinions on what to do about outliers that aren't necessarily impossible but seem very unlikely or very unusual. There are some people who remove, say, the highest and lowest percentage of outliers to just focus on the middle. There are other people who would say, no, as long as you know that the data is correct, you shouldn't be getting rid of outliers because it's real data, it's a real situation you could encounter. So it's very much going to depend on what you're looking for, what questions are you trying to answer, and how certain are you that the data is right, it's just odd. Any other questions on?
In this case, I wasn't watching. What fraction of entries did you throw away to get down to this clean set then?
Okay, so the question was what fraction of data got thrown away in the clean data set, and it was almost half in this example. And so that's, you generally don't, you want to avoid getting rid of as much data as possible. So I got rid of a lot of data here. I was also going through rather quickly trying to demonstrate interesting concepts. But yeah, so an analysis I've run, I wouldn't, if I had to get rid of half of my data, sometimes I would rethink what I was doing. Like, is this the right decision to make? Is there anything I can do to keep more data? It's also going to depend on how much data you have. When you have 10,000 examples, you can get away with getting rid of more data than when you have, a couple hundred examples. Yeah, so the point was, it's depending on what you're looking for. So if you were looking for, if you're interested in infants, you would want to keep the head circumference because that's an important metric. And that's also a really good point that if you narrowed it down to that age range that you're interested in young children, a lot of those entries would have the head circumference, and you would get rid of a different subset of the data. So another very reasonable thing to do would be look at adults and children separately, because a lot of the information is categorized differently, and it might make more sense to have this as two separate data sets, and you could keep more data in each data set that way. Any other questions? Awesome. So that was sort of general data analysis cleaning. So now we have our cleaned data set. Now I want to talk about what you have to do to prepare to actually use that in machine learning. So basic steps are you create training, testing, and validation steps. You do any pre-processing and scaling, decide what to give the classifier, and then select your algorithm. Before we do this, we need to choose a problem. So let's just say our target is the height. We want to predict a person's height based on any other features we have, which right now is their exam completion status, gender, age, education, marital status, weight, and those are whether they did an interview or an exam, and whether or not they completed an exam. And a side note, some of these are probably not relevant. Whether they did the interview or the exam, and whether they completed the exam. But because I later want to show you feature selection, I just left that in here. But if you were really analyzing this data set, you would probably not keep those. And as a side note, this is a great place to point out unit testing, to some degree, is also helpful here. And it has helped me find mistakes that were almost very, very bad. So things like the size of your data sets, the type of data, and some minimum and maximum values. Python's wonderful. It also tries to figure out what you meant to do. So if you have an interesting typo, it might still run, and it might flatten your array, and then it might add it in an interesting way to another array that's not what you wanted to do. And so now you have this weird data that's the wrong shape. You wanted it to be 10 by 5, and now it's 1 by 50. So just a simple unit test, like, is this data what I'm expecting it to be, is really, really helpful and can help with debugging when you don't know why something's not working. It's because maybe your data was the wrong shape. I've done that. So training, testing, and validation sets. This is a way of dividing up your data to try and get a good idea of not just getting an algorithm, but how well is this going to work? So first you have a training set, and this is typically the largest portion of your data, and this is what you use to train the algorithm. You give it to your neural network or your support vector machine and say, learn from this. Then you have the testing set. This is held out. When it's training, it's not allowed to see any of this data, and then once it's trained, you test on it, see how well it did, and that's how you estimate how well your algorithm or classifier would perform in the real world. The third set is somewhat optional. It's the validation set. So this is used if you're trying to select between classifiers, or there's a parameter of your classifier you want to set, or you want to decide which or how many features to give a classifier. So it's like a second testing set. So you would run a bunch of classifiers, test them all in the validation set. The best performing one, you would then test on the test set for your final accuracy. Which leads to the question, why am I splitting my data set like this? The goal of your testing set and testing on it is not to make your testing accuracy as high as possible. It's really not. The goal is to make the real-world target accuracy of your final application, your final product, as high as possible. So the more accurately your test set reflects this unknown, uncertain data that your product will be getting in the real world, the better it's going to be. Another way of saying this is no one cares how good your test set accuracy is if when you ship your product it doesn't work. You can say, oh, but in testing it got 99% accuracy, but if it doesn't work, and that doesn't change anything. All that really means is that your test set was not good. It was not a good representation of the real world, and if it had been, you might not have made that embarrassing mistake of shipping it. So we're going to split. First way we're going to do this is we're going to split the data set, 30% for the test set, and the remaining 70% will be for the training and validation sets. Python makes this super easy with scikit-learn. It's one line. There are your sets. These are the sizes of your data set. You can also set a random state if you want to. This is nice for notebooks like this, so that every time I regenerate this presentation, the numbers will stay the same. You could accidentally select a seed that produces unusual results, and then every time you run it, you get the same unusually good or unusually bad results. And absolutely do not hunt for the seed that works best on your data set. Don't do it. That's called overfitting, and again, it's not going to give you realistic, real-world accuracy. So the first time we used a function called train test split, and it just split the data set. You can also tell it to stratify your data set. And so this is proportionally dividing your target labels between the sets when it splits. The easiest way to describe this is if you're trying to classify animal pictures. You have 1,000 pictures of dogs, 1,000 pictures of cats, and 50 pictures of wolves. You want to make sure there is a proportional number of wolves, this really small class, in all of your folds. Otherwise, you might accidentally only train on cats and dogs, and then it has no way of, you show it a wolf picture, it's not going to know what that is. It wasn't allowed to train on it. And the reverse is also true. If all of your wolves are in your training set, you haven't tested its ability to detect a wolf picture. So right now we're using continuous targets, but we can also bin those into we're doing height, we're trying to predict height, so we can bin that into ranges of height and just try and get it to give a wide ranges of height in each split. So a little more on how to use validation data. This is how you pick your machine learning method. Like we've learned about, there's support vector machines, and we've learned lots about neural networks and regression, but how do you choose one of those algorithms? Additionally, some of them have a parameter that needs to be tuned. SVMs, support vector machines, have a C parameter. How much of your, if you want to decide how much of your data to give it, this is all what the validation data is for. I went over this a little bit before. Why can't I just train all of my algorithms that I'm considering on the training set, test it on the test set, and just use that accuracy? Why doesn't this work? Because that's a type of overfitting. When you select the best model out of many, you're biasing your results towards good performance on that particular test set. So the results will usually be in the ballpark, but they're going to be a little optimistic over how that is actually going to perform in the real world. So a test set, using a third test set on that final selected classifier is going to give you a less biased estimate. And as I said before, that's really what you want. You want to know how it's actually going to work. So when we're splitting so we've already split we have our test set, and then we have a second set of data that we need to split into training and testing. We could split it exactly the same way we did before, and then we have 3 distinct chunks. But we would rather use something called cross-validation. So as we continue to split our data into more and more chunks, we're using less and less of our data when we train our algorithm. But we want to give it as much information as possible, especially when we have smaller data sets. If you're Google and have all the data in the world, maybe this isn't so important. But the smaller your data set is, the more you want to be able to use as much as possible. So the way cross-validation works is it's going to divide your data into many equal sections. And this is best illustrated here. So here, your entire data set is divided into 5 chunks or folds. And so each fold, the yellow one is what you're using as your validation data, and then all of the green folds put together are your training data. And you go through using each fold once as validation, and then you'll have, the average accuracy across all of your validation folds is your overall validation accuracy. But now, you've used all of your data in training, you've also used all of your data for validation, and you've never trained on anything that you then use that classifier for as validation. Yes. OK, so are there any questions on splitting up your data into these different data sets before I move on? OK, cool. So now that we've divided it into our various training sets, some algorithms require you to do a couple extra steps to process your data before it'll work properly. Some will work best or will only work if your features are on a similar scale or normalized to a given range. This is especially helpful for features that have unrelated units and they're very different in magnitude. So for example, for data set about house information, 2 bedrooms, 1,000 square feet. They're very different in orders of magnitude, but they're not very different in terms of importance. But some classifiers will almost ignore the bedrooms because it's a number from 1 to 4, whereas square feet is numbers in the thousands. So if you normalize them to smaller numbers, it helps even out the importance of all the features. So a common example is just setting everything to have 0 mean and a variance of 1. This will speed up training for some classifiers like support vector machines. And another option is sometimes you want to take your data into a range of 0 to 1 or -1 to 1. Some algorithms, like some types of neural networks, still have these requirements that it has to be in this range, or the neurons that were talked about before will saturate in their output. And these things are really easy to apply. Again, with scikit-learn, the most important part is we've already split our data into our training and test set. And so we do this afterwards. So we fit it. There it is. So we fit on our training set, and then we transform our training set, and we separately transform our validation set. So this is still a part of keeping that training data separate from what you're testing on. Any kind of information, including just how the data is distributed, your classifier can't know that about your test data. Another big thing in machine learning is dimensionality reduction. This is reducing the number of features to keep only the most relevant data. Why would we want to do this? It can speed up training because there's less data it has to go through. You'll store less data, which can be important. It can also improve accuracy by getting rid of some of the noise, some features that don't add any important information. It's just taking time for the machine learning algorithm to decide to ignore them. To the main types, you can do feature selection, where you choose a subset of your features, or feature extraction, where you actually create new features to give to your classifier. So feature selection, there's a bunch of different ways to do this. Some are based only on the data. So there's something in scikit-learn called select k-best. It's going to select a certain number of your classifiers based on some scoring function, like mutual information or the f value from an ANOVA. There are also some methods that actually use a machine learning classifier to help determine which, determine which features to keep, such as recursive feature elimination. And which method you want to do, whether you want to use a method that's only looking at your data or a method that's considering your classifier, is going to depend on your particular problem. Are you just trying to find informative information for any classifier? Or if you have an idea of which classifier you want to use, using that in the feature selection can help you decide which features are helpful for that particular classifier. And as far as the code, so this is for recursive feature elimination. You create your classifier. Just here I have linear regression. You give it your classifier, tell it how many features you want. It runs for a little bit because it does have to do some training. But you give it your features and your labels, transform your training set, transform your validation set. And you can even ask it which features it's kept. So the 4 features it thought were important were gender, education, weight, and interestingly, exam completion. It doesn't always make sense why it picks certain things, but that's what it did. The other is feature extraction. So instead of selecting pre-existing features, you are trying to project your features into a different space. So it's essentially a linear combination of your features, and trying to combine them in a way that you can get across the same information in a fewer number of features. Some examples, there's principal component analysis and linear discriminant analysis. Are there any questions about picking your features before I move on? All right. So I know there's a lot in this talk, but I promise I'm getting close to done with the fire hose. So finally, you want to get into how you actually pick your algorithm or your model. So as I've tried to emphasize throughout, this is going to be highly dependent on your data and the problem that you want to solve. So you want to first use human knowledge to narrow it down to a range of possibilities. There's always going to be some method that makes absolutely no sense to use. And then once you've narrowed it down to a smaller range, use model selection with validation to make a final decision. Some things to think about, you can classify, you can use regression or clustering. Which one you pick is going to depend on what type of labels you have, or if you have labels at all. Do you want to be able to explain the operation of what you're doing, or are you okay with it being kind of a black box? Decision trees have a relatively explainable, it's relatively easy to explain what they're doing. It's a tree, they're making decisions on the data, splitting down this tree. You could go and look at the tree and see how it's deciding to do different things. Support vector machines and neural networks are very black boxy. You can try and, people are trying to do things with neural networks to show what each layer is doing, but it's still not as explainable as some other methods. Other things to consider are your speed of training or speed of predicting. So how quickly do you need this thing to train on your data? And once it's been trained, how quickly do you need it to be able to make predictions on your data? Some support vector machines predict very quickly. Decision trees predict much more slowly because they've got to go down through that tree, so as they get larger, they get slower. Neural networks tend to train relatively slowly, but they usually predict reasonably fast. Other things to consider is how complex is your data? Support vector machines and neural networks can handle complex and nonlinear classification that something like linear discriminant analysis might not be able to do. Are there relationships among your features? If you have a pixel, there are relationships between a particular pixel and its nearby pixel, and its nearest neighbors. So as an example, a convolutional neural network is very good at taking these relationships into account. We talked a little bit about those earlier today. Whereas something like a support vector machine is going to treat each pixel much more as it's an individual entity rather than in a relationship to its neighbors. And then, as we also heard earlier today, some networks have memories. Is time information important to you? So for my final bit of this talk, I've talked about using validation to pick, but how do we actually do that? So I want to compare 4 models. They're all going to be using linear regression, but choosing between recursive feature elimination or principal component analysis to choose our features, and choose between whether we want 2 or 3 features to make our predictions. So this is one example. This is RFE with 3 features. And really the important part is we make our folds, we get the data, our training and validation data, we do our scaling, we tell RFE to select our feature, then we train the classifier on the training data, get the predictions it makes to the validation data, and tell it we want the mean squared error of the difference between our predicted values and the actual values. And so we would do this for all 4 scenarios, so with RFE, with 3 features, with 2 features, and then with PCA with 3 and 2 features. And then we look at the results, and RFE with 3 features has the smallest mean square error. The smallest is better, so we decide that this is the model we want to go with. So then our next step is we repeat this on the entire, so it's already used the training data, it's already seen the validation data, so we can retrain the classifier on that entire training and validation. We select our features. And then here we fit it to the entire training and validation set, and we predict on our test set, which so far it has never seen. Get our mean squared error, and then you can see that the validation and testing set have very similar errors. It got a little higher for the test, but not much, which is what we expect and hope to see. That'll be very similar, but maybe slightly higher. And so that is the end of my talk. I hope you enjoyed it. I'd be happy to answer any questions people have on it. It depends on how you look at it. So the more powerful your algorithm is, the more you can get away with not doing as much data preparation. But on the other hand, you're kind of wasting some cycles. If you can repair it yourself, you can get away with a smaller algorithm, which is going to be faster, or that larger algorithm may be able to learn even more about your data because you've cleaned out a lot of the crud and it can focus on what's important. It was interesting. So there was, it's actually not that bad. There's, oh, sorry. How did I make the Jupyter notebooks into these presentation slides? So if I can find, so yeah, so there's instructions on the internet, but you essentially NB convert. You tell it to make a HTML slides from your presentation, and then when you look, this is actually probably better than showing that file. So you can change the view in the notebook, and you can tell it, I don't know if you can see that very well, but there's a little drop down in this view that says, I want this to be a slide, or I want to skip this slide, and you can pick what to show and what not to. And then when you play around with some CSS files to get it, not to make it this big on the screen. But if you want to know, Google Jupyter presentation view, and you should find information on it.
I have a question. In your examples, you work with sort of a canned data set with a code book.
Mm-hmm.
Have you had any experiences or insights on dealing with, say, for example, somebody's system where everything's kind of scattered out in a relational database, and some of the quirkiness that comes with dealing with that?
No, so the question was, this is kind of a canned demo example, and if I had any experience using, data scattered about in relational databases. I have had the fortune and misfortune to work with data that I have collected myself, for good or for bad. So I've never had any experience with that. I don't know if anyone else has that can speak to that, but I'm sure it's fun. So that is a really good question. So the question is dealing with overfitting, and is there a way that looking at your data and your results, can you tell, is this overfitting? I need to relook at it, or is this data, is this valid? I'm going to go with it. The best way to test or to see that is to look at, is to test it on another data set. So if it does well on your validation set, and it does approximately the same way on your test set, it's probably good. I've definitely seen where I've picked a classifier on my validation set, does really well, it does very poorly on the test set, and so that's how I would generally tell that something is overfitting. What was the last part you said?
So you take out almost half of the observation. Have you checked the out observation?
So I got rid of about half my observations, and have I checked why I got rid of them? Oh, have I looked at the excluded ones? No, I haven't. But that is a really good question. If you find yourself excluding a lot of data, you want to look at that and to see, why are you excluding this? For this example, the answer is that I didn't look very hard into ways that I could keep data by, splitting into two data sets or other things like that. But that would be a very good next step. It's like, why have I excluded so much data? How can I keep it? So the question was, have I looked at anything like Google's, it was Google's Refine? open refine as opposed to, say, pandas, because it does, you were saying it does a lot of like exploratory stuff for you. It helps you with that?
Yeah, so it'll help like you visualize where your clusters of data are, like what your variance is between your columns. Really handy.
Okay, yeah, so it helps you, he was saying it helps with finding where your data clusters and a lot of other exploratory information. The answer is no, I haven't, but I'm going to have to because that sounds really helpful. So Google also has something called Facets that has a lot of exploratory and visualization stuff that I will also have to look into.
Just to bring it back to Python and pandas, you can use pipelines in sklearn, scikit-learn to do some of this different pre-processing and scaling and things like that, so you can set that up as a pipeline, so you wouldn't have to go to Google.
So the comment was that you can also set up pipelines in Python so that you don't have to go to Google. In pandas. Yeah. But actually, so I appreciate that comment because I forgot to bring this up. So I was talking about deciding how many features to keep and which features, and scikit-learn has implemented that it will do the cross-validation for you to pick how many features you should have. I haven't looked into it a lot, but unless I'm really wrong on how this works, I would not recommend using that. Going back to this training on your test set, I'm not certain that, so if you want to say both scale your data and then choose how many features, you want to do that kind of all at once. You always want to scale your data and pick your features on the training set and then transform your validation set. So scikit-learn, if you're not certain that's what scikit-learn is doing, I would stay away from those until you're a little more certain, or if you're not using anything else. Yeah, use the pipelines instead.